Before we start Riemann sums, I'd like to spend a little time talking about sigma notation. If I were to write the following, this would be equivalent to A1 plus A2 plus A3 and so on until A sub n. The way I express what I have on the left there is the sum from I equals 1 to n of A sub I. So when we're talking about the terminology here, we refer to I as the index of the summation. AI is what we call the ith term or the general term. And in terms of looking at what is beneath the summation, that tells us where we start in terms of the values of I, and the n at the top tells us where we end. So to make sure that's clear, let's look at some concrete examples. So what I'll do here is I'm going to start off presenting some sigma notation. And what we want to do is make sure we understand exactly what sum that represents. If I were to start with the sum from I equals 1 to 5 of I, we can see our starting value of the index is 1, our ending value is 5, and the general term here is just I. So the way I interpret this is I first note that the beginning value of I is 1, and then I think about how that affects the general term. The general term in this case is exactly just the value of I. So what I get is just 1. Then what we're always going to take for granted here is that I jump from the bottom value, 1 in this case, to the top value 5, and hitting every positive integer in between. So the next value of I will be 2, and thus so will our term, and then it will be 3, 4, and then 5, and I stop there because of the 5 up top. Another sum, if we had the sum from k equals 1 to 4 of k cubed, now my index happens to be k instead of I, but really if I change those k's with i's, this would not change this at all. And when my first index value is 1 here, notice the dependence of my term on that is now saying I take the number 1 and I cube it. When I change my index value to 2, I now take the number 2 and cube it. When I go through this process, I'm going to continue cubing these values until I get to 4, which is my last term there. A small change to this would be if I were to write my general term where I'm swapping the role of 3 and k here. In this instance, as I vary the values of k, notice that that's going to change the exponent. So I start with 3 to the first power, then 3 to the second, 3 to the third, and then finally 3 to the fourth. Just to be clear, we can really have our index start with any value we'd like. My first 3 examples all focused on 1, but I could have the sum from n equals 6 to 8 of n squared. Notice that this would say the first value of n is now 6, the final value is 8. So in this instance, we would simply have 3 terms. And finally, if I have a sum that looks like the following, that of r equals 1 to 4 of minus 1 to the r. We're going to see things like this a lot later in the course where you have a negative number raised to the index value. And we can think about exactly what would happen here. When r is 1, we're raising negative 1 to the first power, and then we go to the second, third, and fourth. And right, we could continue this process. And I should add for all of these examples, once we've established exactly what we're adding together, we also would end up with a numerical value, right? I could simplify that that first one sums to 15. So that would be another way to represent this. So in these examples, it might not be evident why we would want this notation, what is exactly to be gained from what I've written on the left-hand side in comparison to that on the right. I'll point out that this is especially useful notation when we have a long sum so think of something like 100 terms, right? All I have to write is this instead of having to think about 1 plus 2 and then continue this for 100 terms. So there's something nice and concise about what I have on the left. Or when you have sums of variable length, and that's what we're going to see a lot in this course. What if I wanted to represent a sum that has n terms where I don't really want to specify the value of n? This is a nice, concise way. Again, the only alternative is to have some ellipses, which is a little problematic. We don't know what the value of n is, and I'm not making any assumptions about it on the way I represent it in the left. And then what I'd like to look at here, add a page, is just a couple properties of sigma notation. And these are going to be useful a little bit later in the course. So one of those is dealing with constant multiples. So if I have, for instance, the sum from I equals 1 to n of c times a sub I, that's going to equal c times the sum from I equals 1 to n of a sub I. So what is significant here is that a has an index I, so that tells me that a is dependent on the index in some way. C does not have an index on there, so there appears to be no dependence whatsoever on the index. In that case, any such constant can be factored outside of the sum. We're not going to prove this formally, but I do want to give just a demonstration of this so we can see why this would be true. If in particular my C value was 2 and my a sub I was just I, from what we've done above, I know that this would look like 2 times 1 plus 2 times 2 all the way up to 2 times n. Now, just thinking about properties of addition, we can factor that 2 out, resulting in the sum from 1 to n of just this I here. And putting that back into sigma notation, notice that I can put the 2 out front of my sigma notation and represent what is in the parentheses as the sum from I equals 1 to n of I. So that's just a demonstration, and so we can really see how that relies upon our properties of addition. And another property is that if I start with the sum from 1 to n, let's say I equals 1 to n, of a sub I plus b sub I, I'm going to be able to break that into 2 summations. The one that deals just with general term a sub I, added to that deals with general term b sub I. Again, just as an example to illustrate this, if we had the sum from I equals 1 to n of I plus I squared, so in this example, a sub I is I, b sub I is I squared. Let's write this out first. This would be 1 plus 1 squared plus 2 squared, etc. And going up to n plus n squared. Again, thinking about properties of addition, we can rearrange these terms, and I could list this as 1 plus 2 plus dot 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 up to n. Group those terms, and then group likewise all of my squared terms. Now, each set of parentheses can itself be put into sigma notation. And now we see exactly what we claimed was true in our property here for these specific a sub i's and b sub i's. So put that there. And I'd like to finish this video with just a couple things to point out. One thing that's going to come up is that there is more than one way to write, for instance, let's say 1 plus 2 plus up to 10 in sigma notation. But in general, any such sum, there's different ways you could represent it in sigma notation. Probably based off of what we've done so far, the most predictable way I might write this is simply the sum from I equals 1 to 10 of I. But another feasible way of writing this, whoops, is I could start this sum at 0. And then if I wanted to make sure my first term was 1 and I started at 0, then I would have to write this as I plus 1 for the general term. And then I also have to adjust the top number, right? I shouldn't change the total number of terms. So I would need to stop at 9 up there. But by the same token, somebody else might want to start this sum at 2. Then their general term should be I minus 1, and they should stop at 11. And in fact, there are infinitely many choices we could make for where we start that, and we could adjust it accordingly. So I mention this because there might be times where you and a partner are writing down a sum, and it might look like you have different summations, but check and make sure that it's not the case that you really have equivalent, correct ways of writing that sum. And then finally, just a kind of a warning on notation. I've indicated that you can choose any index that you would like, and that is looking at the fact that if I write the sum from I equals 1 to 10 of I, that's exactly the same thing as the sum from I equals 1 to 10 of k. Both of those things represent the sum of the integers from 1 to 10. But a common mistake I might see is somebody writing the sum from k equals 1 to 10 of I. So notice the problem here is I have k in one place and I in the other, whereas in my first bullet point I have consistent lettering. In this instance, I look at I and I see no dependence on k, so it's as if that's a constant. So this would be I, plus I plus I plus I, if I have a constant inside of a sum. And then the question is, how many i's do I write out there? Well, I would write that out 10 times, and that's because of summing from 1 to 10. So in fact, this sum is just 10 times this unknown constant I. That's not the same thing as what I wanted to write above, so you just have to be a little careful. When you are choosing your index value, make sure you're being consistent.